Hi, welcome to a video about proof by induction, in which I'm going to get to using proof by induction on inequalities. But to begin with, let's just consider what induction is by analogy. So here we have three robots, and they want to try and climb an infinitely long ladder. Now the ladder stops here, but you can imagine the ladder going on infinitely far. And we're going to ignore issues about powering the robots and stuff like that, but let's just look at these three robots' attempt to climb the ladder. So first up, the blue robot goes up the ladder, gets on it, so he manages to get on the ladder, but then he's stuck because he cannot get from one rung to the next. So the red robot looks at this and says, I could get to the next one easily. I have longer legs than that robot, so I'd have no trouble getting up to the next rung. So blue robot gets out the way, red robot takes his turn. Red robot goes up the ladder, but he can't get on the ladder. And he's sure if he could get on the ladder, then he'd be able to climb the whole ladder, but he can't get on it. So he gets out the way, the black robot comes along, walks up to the ladder very slowly, and then very speedily gets from one rung to the next, and then one rung to the next, and then so on. So he can do two things, get on the ladder and then get from one rung to the next. Doesn't have to go at that speed, but he can, and that means nothing can stop him from continuing all the way up this ladder. Now, the blue robot can look on and say, I could have done that, except for the fact I couldn't get from one rung to the next. And the red robot, I could have done that, but I just couldn't get on the ladder. And that shows that in order for a robot to climb a ladder, there are two things the robot has to be able to do, and it has to be able to do both of them. If it can't, then it can't climb the infinitely long ladder. So there's really two elements here at play. So hopefully you're recognizing the link to induction. Let me show you it explicitly. So if we're looking to compare a divisibility question, so I'm going to skip all the algebra here and just look at like the structure of the argument. So for a classic divisibility 7, we'd say something like, since fn is divisible by 7 when n equals 1, and if fn is assumed to be divisible by 7, then we can show fn plus 1 is also divisible by 7. We can conclude that fn is divisible by 7 for all positive integers by mathematical induction. So that's a classic conclusion to an induction argument. And by comparison, we're saying since the robot can get on the ladder and get from one rung to the next, the robot can reach any rung on the ladder. A very useful analogy because it helps you see the structure of arguments by induction and apply in novel situations. So you might not have seen an example of induction and inequalities. So I'm just going to stick with my analogy and work through an example. So we're looking to prove that n squared is greater than or equal to 2n for all integers such that n itself is greater than or equal to 2. Now, I mean, this is quite a trivial thing to prove. We could do it in many ways, but let's look at how to do it by induction. To start off with, we'll check when n equals 2, the left-hand side is 4 and the right-hand side is 4. That means the left-hand side is greater than or equal to the right-hand side when n equals 2. And the equivalent is the robot can get on the ladder. Step 1, complete. Next, we're going to assume that k squared is greater than or equal to 2k for an arbitrary k that is greater than or equal to 2. And note, we're not assuming it for all k. That wouldn't be a valid proof because we'd be assuming what we're trying to prove. We're picking one particular one. So the analogy with the robot is to say, imagine the robot can get on the ladder at some point. And then let's do a little bit of work. It's not much algebra, but I'll do it. So let's consider k plus 1 squared. K plus 1 squared is k squared plus 2k plus 1. And now we can look back at our assumption, which was that k squared is greater than or equal to 2k, meaning this k squared can be swapped with a 2k at the price of bringing an inequality sign in here. So k plus 1 all squared is greater than or equal to 2k plus 2k plus 1 per our assumption. That's 4k plus 1. So k plus 1 squared is greater than or equal to 4k plus 1. which is greater than or equal to 2k plus 2. Since k is a positive integer, you could think, if you weren't happy with this, do it more slowly, you could call this 2k plus k plus k plus 1. And k plus 1 is definitely greater than or equal to 2, since k is a positive integer. So we've shown that k plus 1 all squared is greater than or equal to 2k plus 2. Here's where you need a bit of imagination. The reason why I did that is to compare to our initial statement, which appears on the front of the page for k, and we see that k plus 1 all squared is greater than or equal to 2k plus 1. So we're saying if the statement's true for some arbitrary k, it's also true for the next k. So we've imagined the robot can get on the ladder, and we've shown the robot can get to the next rung of the ladder. This means we can safely conclude this on the left of the page. Since the statement's true when n equals 2, true for n equals k plus 1, if it's assumed to be true for n equals k, it's true by induction for all positive integers greater than or equal to 2. Now, it's quite a mouthful. If you're not that familiar with induction, that looks daunting, but hopefully this doesn't. Since the robot can get on the ladder and get from one rung to the next, the robot can reach any rung of the ladder. These arguments are a very nice analogy for one another, in my opinion, or specifically this, an analogy for induction. So, the lovely thing about induction is it's kind of that and so on idea that you're familiar with from everyday speak, and it's manifesting itself in maths and being used to great results. So the next slide, final slide, I'll leave you with this, is a very nice proof, I think, that cos 1 degree is irrational. It uses an and so on type argument and proof by contradiction. So you can pause the slide and have a look at this. It's not very long, but a nice proof, I think, using this and so on idea.